So the idea is, let's say you're multiplying matrices, M1. So these are matrices that are being multiplied together. And so if you remember, so let's just say that, suppose I say M1 is a P1 cross P2 matrix, right? So it's something like, usually we'll say there are P1 rows, P2 columns. So this is M1. Now, if you're multiplying this with M2, what can you say about M2's dimensions? Like if you have to be able to multiply them, yeah? It should have P2 rows, but it can have as many columns. Like number of columns is not decided. So let's just, this is going to be P2, and that's going to be P3, so on and so forth, right? And then times, let's say you have M3, that needs to have P3 rows, but the number of columns could be anything, and maybe that is P4, and then you have M4, which is P4 cross P5. So just to be clear, so Mi is a Pi cross Pi plus 1 matrix. Okay? So the idea is you want to compute M1, M2, M3, M4. So what are the dimensions of this matrix going to be? So this is eventually going to give you some matrix. And remember, this was, P1 cross P2. This is P2 cross P3. This is P3 cross P4, and this is P4 cross P5. So what are the dimensions of the final matrix going to be? Yeah? P1 cross P5. Right? Because when you multiply these two, you get P1 cross P3, then P3 cross P4, so on and so forth. So you end up with a P1 cross P5 matrix. Okay? So the dimensions are all different. So some matrices might be smaller, some might be larger. So let's look at how many operations to compute M1, M2, M3, M4. So let's just start with M1, M2. Okay? So I'm going to remind you, we'll just sort of go over, which you may have learned in either high school or some undergraduate linear algebra course, is how do you multiply matrices. So this is P1 cross P2, and this is, let's say, P2 cross P3. So this is M1, this is M2, and this is the product matrix. So to get any entry of this matrix, so let's say you want the ijth entry over here, what do? You're going to take the ith row over here. You'll take the jth column, right? And then you take a dot product of those. Right? Does this sort of kind of look familiar? So you're going to take all of these entries and all of those entries. And this is a row vector of dimension P2. That's a column vector of dimension P2. So they have the same dimension. And so you can basically take the dot product of those. Is that? Yeah? So how long would it be to compute that dot product? was simple. Just like run a for loop, how much would it take? P2. It takes O of P2, right? Because there are P2 entries, so it's O of P2. So I'll just say it's O of P2 time, or it's even simpler to compute the ijth entry of the product. And it's even simpler, it's exactly P2 multiplications. It's exactly, you're taking these entries here, and multiplying. By the way, who do you think actually needs to multiply matrices? Like large matrices. Do you think people actually do this in practice? Where? AI. Pretty much every single AI thing that you've heard of, you've used, whatever, is all multiplying a bunch of matrices in the end and doing more stuff on top of it. But matrix multiplication is like the most you know why NVIDIA makes so much money? Why are they worth $1 trillion? And they lucked out. Basically, why? They didn't build AI chips to start off with, right? I mean, I'm assuming you all know what NVIDIA is. And you all know that they make tons of money, and their stock is like, well, it dropped a bit, but it has shot up like crazy because they built GPUs. What is the full form of GPU? Graphics processing. It's not AI processing, right? It's graphics processing. Because in graphics, you have to do a lot of matrix computations, right? Usually when you're rendering a scene, there's a lot of matrix multiplication going on. And it turned out that all this AI was using matrix multiplications, and they realized, oh, you could use these graphics units to actually do it quicker. And so essentially, they ended up being on this gold mine. Like, NVIDIA did not plan to make AI chips. They were doing graphics chips. And the reason why a lot of that is so useful is because multiplying matrices is so common. And actually, this thing that we're going to do is going to show you why it's such a big deal. Okay, so we said to compute each entry is P2 multiplications. How many entries are there total in the product matrix? How many entries in the product? Yeah? P1 times P3. Right, so there are P1 times P3 entries in the product. And so if you look at it in total, we need P1, P2, P3 multiplications. The reason why I'm counting multiplications is it turns out, and we're going to see this actually later on in the course as well, that when it comes to like if I give you two bit strings or if I give you two numbers and say like sum them, that's usually pretty easy. But to multiply them takes actually a lot of time. So it's in multiplication that all the optimizations happen. So let's just count the number of multiplications it takes. And that's like our measure of runtime. Okay? So in total, we need P1 times P2 times P3 multiplications. Now, if you think about it, that's actually quite a bit. Because if in like AI settings, usually your P1 and P3, like they could be like, billions, millions. Usually matrices are often like short, like they're either like thin and tall. So P2 might be small, like 1,000, but P1 might be like 1,000,000. And so you're actually multiplying all of these. So you get lots and lots of multiplications to do, right? And saving on this is important. And we'll see that for this problem, okay, so now let's go back to this M1, M2, M3, M4, right? This product. So we said to compute M1 times M2, you need P1, P2, P3. Once you do this, you're going to have this matrix, and I'm just, for convenience, I'm just going to call it M12. And this matrix is a P1 cross P3 matrix. this is P3 cross P4 and P4 cross P5. So then you do this multiplication and you end up with P1, P3, P4 operations. Does that make sense? Right, just by the same logic. You're just multiplying all the dimensions together. Right? And so then that gives you this new matrix here, which I'll call M123 times M14. And so this is a P1 cross P4 matrix, and this is P4 cross P5. And to multiply this, you get P1, P4, P5. That's the number of operations. Like this is the number of multiplications. Multiplications to compute M1, M2, M3, M4. Okay, so does this make sense? But is this the only way to compute this product? Yeah, what could you do?
Like multiply M3 by M4 first.
Yeah. You could multiply M1, M2, then M3, M4, and then multiply those two together. So let's just look at this. So what we've done over here is really use the associative, or rather, we've basically computed it this way. But you could also compute this way. And if you did it this way, so I'll just write down the number of operations, the number of multiplications is going to be P1, P2, P3. For this one, it's going to be P3, P4, P5. And then you get P1 cross, and then you get P1, P3, P5. So if you look at this expression here and this expression here, the first term is the same, but the others are different. And it's not obvious which one is better. Intuitively, if you did it this way and this created a smaller matrix, then it's better. Does that make sense? So you could parenthesize this operation in many different ways. You could also try M1 times M2 times M3, M4. Right? Does that make sense? So I think, or you could also do M1 times M2, M3, M4, and this you could parenthesize. Let me see, you could do it this way. I could do that. Is this making sense here? And for each way of parenthesizing, you'll have some different number of operations to do. And the question what is the most efficient multiplication method, which is the same thing as the best way to parenthesize the matrix multiplication. So does the problem make sense? So think of the input not necessarily as the matrices, but really just the dimensions of the matrices, because that's the only thing that matters. Yeah?
Sorry, so in that second line, right, the one right above the question where it says number of multiplications, we're saying that regardless of how you parenthesize, you will always have that number of multiplications?
No. This is the number of multiplications for this parenthesization. This is the number of multiplications for this parenthesization. So every way that you parenthesize, you could probably write down how many multiplications you need. Like if you do, for example, this one, the first one is going to be P2, P3, P4. Then you're going to do like, P1 times, I think, P2 times P4, and then so on and so forth.
Well, it looks like the number of multiplications is the same, it's just the combinations are different.
No, the number of multiplications is not the same, right? So these are two different expressions in P1, P3, and P4. This is P1, P2, P3 is the same, but then it's P1, P3, P4. Maybe it's worth drawing an example. So let's do an example. Okay, let me see if I get this right. Yeah, okay. So let's say you have some matrix here, M1. Excuse me. And M2 is like this, what they call a tall and skinny matrix. Is this going to check out? Yeah, it is. It is going to check out. Right? It's a really tall and skinny matrix. And then M3, this is called like short and fat matrix. Times M4. So this is the sequence of matrices that you have. Okay? So what you want is, if you actually think about it, if you multiply M1 and M2, you also get a tall and skinny matrix. Right? So if you multiply M1, M2, M1, M2 is going to have something like this. M1, M2 is going to look like that. And M3, M4 is going to look like that. So the question is, like, it seems like you would like to get these like really off-sized matrices in the middle so that you can save on calculations. So if you did it just one by one versus if you did it some other way, the number of multiplications could be different. Does this make sense? So for example, suppose you decide to multiply M3, M4 first. M2, M3 first. You get M1. Now, M2 times M3 is actually a big square matrix, right? Because there are lots of rows here and there are lots of columns there. So you end up with something like this. So that was like a bad choice to start off with. Instead, it may have been better to do M1, M2 together and then M3, M4 together, because then you get these smaller matrices. Of course, then you have to multiply this. So it's not excuse me. It's not obvious which way. I mean, okay, in this picture you can see that clearly multiplying M2, M3 first probably wasn't the best choice. Does this make sense? So the right choice, I mean, okay, it depends on what these expressions are, but you can write down. So maybe I'll just write this down over here. So M1, so I'm writing down what it costs to do this parenthesization. And maybe just to keep it simple, just so that, there are less things to worry about, I'm going to think maybe these matrices were square of the same dimension P. Just to keep it simple. And this is, maybe this is Q. Okay? So let's see what the expression is for this one and what the expression is for this one. And then we'll... So for the first multiplication, you're going to get P square Q, right? P times Q. And for this multiplication also, you'll get P square Q, P times Q. And then finally, this is actually P, Q, Q, P, And again, you'll get P times Q. But if you did it this way, what's going to happen is that this is actually going to be, it's going to be P square Q to compute this. It's P times Q times P. But then these are all like P cross P matrices. And then you're going to end up with plus a P cube plus P cube. So this is much better because you think Q is much smaller than P. Right? So this way of doing it is going to save you operations. If you did it this way, it's actually going to be more expensive. Right? Does this example help? So depending on how things are like short or skinny, tall or fat, there are different ways of doing it. Yeah?
So it's just about reducing the dimensions, like iteratively?
Yeah, so you could think of it that way, which is like you want to try to get the matrices to be smaller in between so that things are faster. But again, what I'll show you is instead of trying to think about, what is the algorithm that will do it, there's a dynamic programming solution that just solves the whole thing without you having to worry about figuring out what the best way of doing it is. Yeah?
If all the matrices were squared,
It doesn't matter. Exactly. If all the matrices were the same dimension, then you'll see that no matter how you do it, each matrix will cost you P times P cube, and then you're just summing up the number. So it'll be P cube times whatever, I guess, n minus 1, which is the number of multiplications you need to do. Or whatever, k minus 1, if there are k matrices. But if the dimensions are all different, then it's not so clear. Okay? And again, this is, one of those examples where you look at this problem and you might think, okay, the most natural human way of thinking of it is usually to come up with a greedy heuristic. Which is like, I'm going to try to multiply so that the matrices are going to be as small as possible, and then try to sort of chain it together, but maybe based on one decision, there's another decision that changes, and so it's quite hard to argue that what you're going to do is correct. You can come up with an algorithm. And it's the same thing with this like optimal binary search tree thing. You think about it a bit, you'll say, okay, I'm going to make the most common element of the root, and maybe I'll do something with that. So it's natural for us to think in terms of greedy algorithms. But for this problem and for the other one, as we discussed, there's an optimal solution based on dynamic programming. Okay? So that's what we'll see. And you'll see that, you say, how do you know that you can use dynamic programming here? And again, it's sort of habit of trying to look for the pattern of recursion. Like, is there a recursive way of breaking up this problem? Okay? Does this question make sense now? Okay. Actually, now that I have this, I should put in page numbers. 47. Okay. So suppose you have the sequence M1, M2, all the way to Mn. Now, one way of thinking about it, like in these examples, is, again, our way of thinking about it sort of, let's say, bottom up would be like, what is the first set of matrices, pair of matrices you want to multiply? But that's actually not a very good way of breaking it up by recursion. So think about, what is the first higher level decision you should make when you want to break this up? Yeah? So I'd say don't worry about the smallest one right now. I want to sort of just build a recursive algorithm that's just going to try all possibilities. Yeah?
maybe we could find some point and like split
Okay.
and then multiply
Both sides. So instead of thinking about the first one, suppose you think of a split. Because in the end, there is the last pair of matrices that are multiplied. So instead of thinking of the first, think about the last decision. So in this case, you split M1, M2, and then M3, M4. In this case, you split it as M1, M2, M3, and then M4. Here you did the same split as this at the highest level. And here you split M1 and M2, M3, M4. Yeah?
So like a sliding window kind of to divide this problem?
It's even simpler, right? You just choose a point in the middle. You just choose one point, break it into two parts, recursively find out the solution for each, and then you see which of those splits was the best. And that'll give you a recurrence. And once you write that recurrence down, the dynamic program is actually pretty obvious once you do that. So I'll re-emphasize this because this comes up a lot. We'll do greedy algorithms next, but which you may be familiar with. But in greedy algorithms, it's easier to come up with the algorithm, but harder to prove that it's correct. In dynamic programming, it's the opposite. It's hard to come up with the algorithm, but once you come up with it, you know it's optimal. Okay? And so it's a lot of how do you come up with a dynamic program? It's sort of practice, and it's looking for this pattern. It's looking for this pattern of recursion. How do I split this problem up into two recursive parts that I could solve? And then recognizing the overlap. So let's do this. So, as was correctly said, you could think of, suppose I split this way. So you can recursively get the best solution or the parentheses for each part. And suppose then how much does it take to multiply? What are the dimensions of this matrix? The dimensions. So again, remember the dimensions of each MI are like PI cross PI plus 1. What are the dimensions of this matrix? PI cross PI plus 1. It's like PI cross P2 times P2 cross P3, P3 cross P4, but all that middle stuff sort of goes away. It's PI cross PI plus 1. Right, so this gives you a PI cross PI plus 1 matrix. That's what you get from here. And what are the dimensions of this matrix? Sorry? No. You have to say it in the right order, right? PI plus 1 cross PN plus 1. But this is a Pn cross Pn plus 1 matrix. Yeah?
On the left, is that P1 or PI?
P1. It's P1 cross Pi plus 1, Pi plus 1 cross Pn. So to do this multiplication costs you Pi plus 1, Pn plus 1. So what this means is that if I figure out how to do these recursively, I know how to get the number of operations for the whole thing. And all I have to do now is to minimize over all possibilities. Okay, so I'm going to write this out. I'm going to write out a recurrence, and then I think you'll see what's going on. So I'm going to say that this is I'm just going to build either a table or a recursive function, which I'll call the least parentheses, which is the least number of multiplications, or I'll say entry multiplications for computing the matrix product, right? And so here's my recurrence. So I'll say LP of, let's just do from 1 to n, is going to be the min. So I choose all possible splits in between. LP 1i plus LP I plus 1n plus P1 Pi cross Pn plus 1. Does that make sense? So for all choices of I minimize this. Yeah?
Sorry, can you put a dot over the I
Yeah, sorry. Yeah. Right, does this make sense? This is the least parentheses. You choose a split. Of course, I'm going to write the recurrence a little bit more properly. This is just looking at like the top level case. But really the right recurrence is the following. It's if I take any I and j, then it's the min over all you see if I need to do my indexing correctly. So the k, okay. So you'll see technically it's j minus 1 because I can't split there, I have to split before. Right, so actually this should be n minus 1. Okay. So what you get is the least parentheses from I to k plus the least parentheses from k plus 1 to j plus pi, pk plus 1, pj plus 1. This is your recurrence. And as is for a base case, what you'll have is that this is just 0. Right? So this is saying that if you're just looking at one entry, one matrix, there's nothing to multiply. It's 0. This will now you look at this and you can say, oh yeah, I can see there's a table. Does that make sense? Right? So again, I've written this as a recurrence, as a recursive function, but obviously you can replace this by a table. And then you just fill up the table. Question?
Yeah, I'm just not getting what happened like in the leaves, like the return models.
What happens in the leaves? Leaves just return 0.
Well, yeah, but the upper.
So if you look at what is 1 above a leaf, it's just multiplying 2 matrices.
Yes.
And that is this term here.
Yeah, so there comes my question. Why 3 multiplying?
Because if you multiply any 2 matrices, you get, yeah. Does that make sense?
That's like the same case as optimizing binary search tree. It's more or less the same.
It's not, I mean, it has I mean, the expressions are different, but it is a similar idea. It's a similar idea that there's a split in between. You do something for one half, the other half, you put it together, you add some term, and then you take the sum. So that's one of the reasons why I like this example with that, because they both have the similar, it's like the similar, you're actually optimizing over parenthesization in both cases in some way. Yes?
So for the top one, P1 plus PI plus 1, and then the other one is PI plus 1 cross PN plus 1?
Yeah.
Why is it the first one is PI plus 1 and not PI?
Okay, so if you look at just multiplying M1 times M2, the matrix you get at the end is a P1 cross P3 matrix. Maybe it's worth looking at this example. So if you look at this, it's a P1 cross P2 matrix multiplied by a P2 cross P3 matrix. When the product is P1 cross P3, that middle P2 kind of disappears in the product, in the dimensions of the product. It's still part of the number of multiplications you need to do. The number of multiplications you need to do is P1 times P2 times P3, as we said here. That's the number of multiplications, but the dimensions of the product are independent of P2. Does that make sense? The dimensions of this product don't depend on the dimensions in between. So the dimensions of the product are what matter for essentially determining what is the cost of multiplying the number of operations or multiplying the final thing. It's like saying that I don't care how you multiply these things together. Do it whichever way you want. But in the end, you still have to do a P1, Pi plus 1, Pn plus 1 operations to get the final product. And so that's what's being added over here. Does that make sense? Yeah? So this gives you your recurrence now. So you see the overlapping subproblems. Right? So I'm not going to write out the full table because by now hopefully you kind of get the basic pattern. But in your homeworks, whenever you solve a dynamic programming problem, you have to write this. This is what you need to write. You need to write, this is the recurrence with the base case. Okay? And then you can explain what the table is, because the table is pretty obvious to explain then. And then you explain how do you fill up the table, what order. Yes?
So for homework 3 and coding homework, do we also need to explain
No.
it, or do we just need to code the table?
You just need to code it up. For the coding, you don't need to explain the table.
Can we just build the table, sorry for that, just to have another example?
Yeah, okay, sure. Let's go ahead and fill the table then. Yeah, sure. Okay, so here, like the dynamic programming table. So I'll just do this. I'll write this as the table. So this is going to be an n cross n table or array, whichever way you want to look at it. And you can see that sort of the right order to fill the table is in the difference I minus j, or j minus I. So let me fill out the table in this way. So just to do, what is the base case? The base case would be just, for I in, excuse me. So I guess I've been labeling this 1 for I in 1 to n. We'll just set LP of II is equal to 0, right? That's the code that you would do for that. And then filling up the table. So we'll say for I in 1 to n, I'll say for size in 1 to, I guess, okay. So I'm going to write this. It's going to have a few indexing errors, and then we'll just go back and fix the indexing errors. That's not going to be as important. So what I'm going to say is we'll set j is equal to I plus size. Right? So that's like the j that I'm looking at. And then I'll just have this additional thing that, if j is greater than n, then just continue. That just fixed the indexing, right? If j is more than, if I plus size is more than n, just ignore it. No need to do it, yeah?
What is size supposed to represent?
It's j minus I. It's like the size of the interval that you're looking at.
Okay.
Does that make sense? I mean, I don't know if size was the right term, but it's like saying that the way that really this is being broken up is like you're breaking it up like that. This is my size. Okay. So now once I've determined my I and j, now I actually have to do the minimization. So I'll say for k in I to j minus 1, okay, so I guess I have to store the min. Let me write something down and then I'll just fix the code. So when you do this option, what you get is LP IK plus LP k plus 1j plus PI PK plus 1 PJ plus 1. Right? That's how many operations you get. So I'll say this is my candidate. And I'll say if the candidate is less than the min, then I'll just set LP ij to be the candidate. And for convenience, I will just initialize the min to be infinity to start with. Right? So you can implement it however you want. But the point is, you just start by saying that, okay, you just start with some value of the min, which is just infinity, and then you go over all choices of k, and if your candidate is less than the minimum, then you just update. Sorry, yeah. I should say, okay. Let me do it. Let me just initialize LP ij to be infinity, and then say if this is less than LP ij, then do that. Right? So I don't need to, I'm just storing the minimum implicitly in that. Does this make sense? So this is how you'd fill up the table. Now the table does not give you the actual doesn't tell you the best way. For that, you have to store what is the option. So you have to store the k that actually does this minimization.
Just a little bit. When we read this, can you put like the formula, the initialization of size, j minus I?
Sorry, maybe I'm missing something.
Yeah, if we have to initialize size.
No, but size is a loop variable.
Yeah, but it doesn't go over all one, two, oh no, yeah, it goes to, no, sorry.
Yeah. Does this make sense? Yeah? You can eat, that's fine. Yeah, is that clear? Blood sugar is always good.
Does the NVIDIA is using this dynamic programming method for measuring multiplication?
Sorry? Is NVIDIA doing it? I don't think NVIDIA does it. NVIDIA builds chips, but people who are writing code on top of it might, in some cases, do that. Like, especially, I would imagine that if you ever use MATLAB and you tell MATLAB to multiply a bunch of matrices, the compiler would probably do this optimization. So all of these are probably built in the compiler side. Like, even if you're just multiplying 3 matrices together, you could do the first and the second times the third, or the first times the second and third. Just that choice is probably done. Yeah? Yeah? Question? Am I mistake?
For I on the outer loop and for size is the inner loop. Does that work, or should you iterate over the sizes of the outer loop and the I as the inner loop?
You're right. Sorry. You're right. That was a mistake. This is what happens when I write code on the fly. Thank you. Right? Good point. You first go over the size, and then for each size you go over all I. Thank you. So the way of thinking about this table is if you have I and j, again, you only care about the case where I is less than j. So it's really, okay, so the way I usually like to do it is, this is going from n all the way to 0, or n all the way to 1, n all the way to 1. And so this is the entry that you really care about. All of this can be ignored. And so the base case is this diagonal, where I is equal to j. And you're filling it up sort of in this way. Right? So the table size is O of n squared, where n is the number of matrices. The running time is O of n cubed, because there's n square size table, and then there's an extra loop over here. This is an extra O of n loop. Right? To basically go over the options, and so you get n cubed in total. Yeah?
What is, so it says, after the O of n group, it says TM?
Candidate, yeah. It's just some variable.
Sorry, okay.
It's just some variable. So what I am not telling you is how do you actually get the optimal parenthesization? But you'll see it's the same logic, it's just extra 2 lines of code that you need to put here. That is, when you're updating the min, you also say, oh, this means that I should split at k. Does that make sense? Right? So to get the optimal parentheses, you need to store the k that gives the minimum. Okay? All right, so let's take a break for a few minutes now. And then when we come back, there's one more topic on dynamic programming I want to talk about, and then we'll wrap up dynamic programming. Okay, so I guess, sorry, I should have mentioned one thing. Someone pointed out that this table was messed up. So the index is going 1 to n this way and n to 1 in j. But whatever. The important thing is it fills up sort of diagonal by diagonal. So any questions about this? Is this example clear? And hopefully if you go back and look at that binary search tree example, it'll make a lot more sense because they're quite similar. Multiple people have asked, like, how do you exactly come up with a recurrence? And I don't know. I mean, I guess it's practice. It's kind of it's looking for this pattern. Though,
I just have a huge concern. I understand it after you explain it and after you think over it a lot, but if you put something like that, like in the midterms.
no, I'm not going to basically throw out something crazy like that on the midterm. At least I don't think. No. I think the point is to do the homework. And the other thing is if you've solved homework 3, so homework 3 is not that difficult, but go and look for this pattern in homework 3. You'll see it. Like, it's there.
My only concern is homeworks we have time to study.
Sure, no. I mean, I'm not going to give, the midterm is not, by the way, I should clarify. The midterm is going to be, it's multiple choice. It's like maybe 10 questions, multiple choice. If you know what you're doing, it should take you half an hour. It's not, I'm not going to make you come up with like really complicated things in the midterm. But definitely do homework 4 where you have to do many of these. And whenever you write the solution, write it in this way so that you know exactly what you're doing, right? So there are all the steps. There's the recurrence, there's the base case, there's the table size, and the review time. So of course, my code over here might have indexing issues, and if you write something which has indexing issues, it's completely fine. I'm going to ignore that, right? It's instead better to explain, like just say the table is, filled up diagonal by diagonal. So what I need from you whenever you get a problem is you first write the recurrence and just give like a 2 or 3 sentence explanation of what the recurrence is doing. Okay? Of course, I have written like all of this stuff, and I'm not going to give you as complicated as a problem. But give the recurrence, the base case, give a short explanation, 2 or 3 sentences. Write down what the dynamic programming table is, and explain how to fill up the table. You can give pseudocode if you want of this form, or you can even just explain it in words. That's fine. And then give the table size and give the table runtime. That's it. And I promise you, if you do like 10 of these examples, after that it becomes pretty clear what's going on. You just have to do multiple examples. Question?
Sorry, can you clarify what you're referring to? Is this like something I'm looking for in the homework, or just like in general?
This is how to solve the homeworks. How you should write down your solution for the homeworks. Just how you should write your solution for your homeworks. But in general, if you're also explaining a dynamic program to someone, this is sort of how you would do it. You say, here's my recurrence, and then here's how I'd fill up the table. Right? And it's kind of like, I don't know, like most things in like the theory of algorithms, right? It's like a new way of looking at things. It takes time to get used to, but once you get used to it, then that's another tool that you have. So you have all these different, like just like, you start recognizing, how do you recognize what data structure to use? Like initially it's pretty opaque. Like you have all these data structures, you're not sure. You start seeing the patterns. Okay, I have to do some extract min, probably I need a heap. Or, okay, I'm doing some kind of search, maybe I need this kind of hash table. So it's about recognizing this pattern. So when you see this sort of recursive pattern, or rather you should even think, when I see a problem, can I do dynamic programming on it? Like if you just ask yourself that question, then you'll force yourself to think in this way. In some cases you can, some cases you cannot. Okay? But I've tried to give examples in the homework of that kind. Let me see, maybe what I'll do is I'll put out even more questions, which I'm not going to grade, but as exercises for you to do. And so you're always welcome to come and ask me in office hours about them. Yeah?
Can you also post
I will, but after the homework gets created. And no. So the book, CLRS, actually has a, I mean, okay, so the book is a bit pedantic, meaning that it's just a lot of text, and it's a bit dry. It's not the most interesting book to read. But I think once you get this, if you go and look at the book, it'll make a lot of sense. I promise you that now, if you go and look at the book and you see the solution, it'll be pretty clear. Okay? Yeah?
I had a question on the previous page. There was this, why is it specifically in the recurrence part, the minimum of I, which is less than equal to k, which has to be less than equal to j minus 1? Like, why can't it be j?
You're not minimizing over I or j, you're minimizing over k. K is the loop variable.
Oh, okay.
You're minimizing over k, and these are just the bounds for k. I and j are fixed, right? There are arguments on the left-hand side. You're just looping over all k. It's like looping over all splits. Okay? Okay, so now I'm a bit... Did you all see dynamic programming in an undergraduate course? Like 102 or sort of, kind of? Okay. So this is more in depth than that, I'm guessing? Okay, all right. How many of you did it in 102? Just out of curiosity. 1, 2, 3. No, I'm not going to quiz you on that. I'm just genuinely, I'm trying to understand, because if there is something that we should be teaching there and we're not covering, or if there's something that, we could maybe spend more time on dynamic programming there, that would be useful to know. Okay, so far so good? I'm going to do one last example, and unfortunately this is a more abstract example. But what it does is it sort of covers all possible dynamic programs in some way. So it turns out that there's a problem called, which I'll just refer to as path optimization over a DAG, right? So you have this problem of G is a DAG, and let's say edges have weights. Three, 42, 101, whatever. And so the problem is find the longest path. So not shortest paths, but find the longest path in a DAG. That's the question. Make sense? So there's obviously some path that's the longest. How do you find the longest path? And this is actually also a classic dynamic programming problem. And again, this is one of those situations where it's not obvious. You look at it, you're like, well, longest paths, maybe I do some sort of breadth first search or some depth first search or something like that. And this is where, again, okay, so this is, you start looking for these patterns. And one way to frame this is to say, suppose I want to compute the longest path, V, which is the length of the longest path ending at V. So let's say I have some V over here, and I want to get the longest path that ends at V. So if I can compute this function, then I can just maximize over all V. Yeah? How do I compute this function? Can I do it recursively in some way? Yeah? Yeah?
More or less the same as we were looking like. Just start from some point. Just get all the starting points, possible starting points. That would be 1 to n. And start splitting.
But it's a DAG. It's just a bunch of vertices in a graph.
Well, but the splitting is neighbors.
Okay, so how do you write? So exactly, it's something to do with neighbors. What is the recurrence you would write over here? Yeah?
Max for all in
Okay.
neighbors.
Yep. So look at all in neighbors of V. So look at all U, which is in, I'm just going to write this as N minus of V, which is just in neighbors. Right? So you're looking at all of these U's. Okay, and?
Longest path U.
So you do longest path of U. Okay, wait. So I think you know. So now someone else tell me. How do I finish this, right? So this is exactly the logic that you need. So it says, how do you get the longest path to V? Well, you look at all of your in neighbors, because any path that goes to V has to go via one of your in neighbors. Look at the longest path to those, and then what? Yeah? Plus UV. Plus, I'll say the weight of UV. Right? Yeah? Okay. So these are all the in neighbors. Okay. So this is a recursive algorithm. Just ignore dynamic programming or anything. Will this recursive program actually terminate? What is the base case? Well, I mean, so you're going to do this recursively. This is going to call a recursive function for U, and U is going to call a recursive function for its in neighbors. Where is the base case? What's going to eventually happen, yeah? If you have no in neighbors, and that is called a source. So the base case is for V that is a source, which means it has no in neighbors, longest path of V is 0. Now, if this was not a DAG, let's say it's an undirected graph, what would happen to your recursive algorithm? Yeah?
You could go back and forth on the same edge internally.
You could go back and forth, or you could just loop. If it was directed, you would keep looping. But because it's a DAG, you're not going to loop. This is going to terminate. Yeah?
Would there be multiple sources?
There could be multiple sources, yes. Because it's just longest path, you don't know from where, you don't even know what the end of this path is going to be. It could be anywhere. Right? So this makes sense? So you can see that this recursive algorithm is going to terminate. But if you, now suppose we do it in terms of dynamic programming, we could build a table. Right? We could build a table. So if we look at the dynamic programming table, question, what is the order to fill up the table? Yeah? Yeah, how do you find the source nodes? But there's actually this specific one phrase, 2 words that I've mentioned in a previous lecture. What is the order? Yeah?
Topological.
It's a topological ordering. If you fill it in topological order, you'll always fill up the table. Does that make sense? It's a topological ordering. So now your answer, how do you find all the sources? If you just do a topological ordering, then automatically the sources will be before everything else. Right? So essentially, it all sort of comes together like that. So let me write this out. So, start with weighted DAG G, compute a topological ordering. And so this is all linear time, right? O of m plus n. And fill up the dynamic programming table in that order, in the topological order, according to the following recurrence, which is longest path of V is like the max of U in the out neighbors is the longest path of U plus the weight of UV, and the base case, as we said, the base case is longest path of V is 0 if the in neighborhood is empty, if there are no in neighbors. You can even check this, like technically you could even just do, you just look at the adjacency list.
So for the algorithm, you first have to find a topological order.
Yes.
DFS.
Yes. You first do DFS, you get the topological ordering,
And then we go.
then you go in that topological ordering and you apply this recurrence. So you can do it essentially, the total time is O of m plus n time to compute the longest path. Is there anything we used about the fact that it's longest? Could we do shortest? Could we do like shortest paths? Let's say shortest path to a vertex. You could just replace that with a min, you get shortest. If you replaced it actually with some kind of a sum, you can even compute the number of paths. So you can do all these different optimizations on a DAG. These are all path optimizations on a DAG. So whether you do min or max or sum, you could put any function over there and compute it. So this is a really important fact to know, that anytime you have a DAG and you're trying to do something with paths, usually there's a dynamic programming solution. The ordering of vertices is a topological ordering. Okay?
Can you put the, I guess
That?
or the order of solving the problem. So yeah.
Okay, yeah. Okay. Let me just number these. T3. 52. Okay, so does this make sense? Okay, now I'm going to tell you something. So, is that clear? Now I'm actually going to claim that every dynamic program that you've seen, or anything that you'll solve, under the hood is actually optimization over a DAG. And the orderings that you find are actually topological orderings of that DAG. Even though you don't see the DAG and you kind of go, oh, it's column by column or row by row or diagonal by diagonal, there's actually a DAG hiding there, and that ordering is a topological ordering. Okay? It's not that hard to see that. So what are the entries of your table in a normal dynamic program? What do the entries represent? Yeah? Yeah? Indices. What are the indices? Yeah, they're indices, yeah?
The optimal solution at that index.
That's what's in that table. But what do the indices represent? It's arguments, right? It's arguments, I'll write this out, but I want to say this. It's arguments of some function. That's what each table entry represents at some level. No, don't think about, so think about, let's go back to, let's say, this dynamic programming table that we did. Right? So you have this recurrence over here. I and j are the arguments. So suppose I built a graph. And I built a graph where I have one node for every entry of the table. Right? And I put a directed edge if one makes a recursive call to the other. Does that make sense? So I build a graph where every node is now I comma j. And I put an edge from I comma k to I comma j if you have to solve I comma k first. So if it's like the recursive call. I could build a DAG. And that's like the recursion tree, but it's like a recursion DAG. Does that sort of kind of make sense? And you're basically doing, there's a DAG there, and the ordering is a topological ordering there. And this might seem a little weird, but actually any sort of distributed system, any system that is dealing with lots of recursive calls is doing that. Under the hood, the compiler will build a DAG of all the things that need to be solved, and then solve it in topological ordering. Right? If you think about how recursion works, it's all about there being a bunch of processes and there's a dependency between them. And the topological order tells you how to process them so that you don't break the dependencies. And it's the same thing going on with dynamic programming. So all dynamic programs under the hood are effectively building a DAG and solving them in topological order. Okay, so let me write this down. Okay, so I'll say, consider any dynamic program, right? Build a graph, actually it's going to be a DAG, where each node, I'll say vertex, is a table entry. And let's label it by the arguments it represents. So, for example, I would do like I comma j, I comma k. So for the previous example, right, I basically take the arguments and I make a node, make a vertex for every argument. Okay? Now I'll put this edge. What does this mean? It means, so I, j are the vertices. Okay? What this means is to solve ij, we have to solve ik first. It's exactly what this is saying, right? So if you want to get what ij is, you first have to solve all of these. So you do ik, and whatever, maybe over here you'll get some k prime j. You've got a bunch of things that point to it. And then these have a bunch of things that point to it. This forms a DAG because there are no loops in recursion. I mean, if you add a loop in the recursion, then your recursion is broken. Right? So you have this DAG of all the arguments of all the entries, and you process in topological ordering. Now, you're not computing the longest path or shortest path, you're doing some other weirder path function. But you can think of this is like an edge weight. And every dynamic program will sort of have this feature, right? There's some kind of edge weight or some quantity, so that you'll take a bunch of things from the recursive calls, you put in the edge weight, you compute some function that minimizes over everything, and it's all a topological order. Yeah?
The matrix is like the edges.
Sorry?
The matrix feels like the edges.
The matrix is actually the vertices. The edges are when you want to fill up an entry, what do you have to look up? It's the lookup. So when you want to fill up ij, you're looking at ik and k plus 1j for all values of k. Those are like, the edges are like from here you have to look at these. So that's what these edges are representing. So you can always convert a dynamic program into this form and solve it using a topological ordering, although it's kind of, there's no point in doing that code-wise. But conceptually, that's why optimization over DAGs is called a canonical problem. It's like a fundamental problem of dynamic program, because everything in some sense is just doing that under the hood. Okay? So, does this sort of make sense? Again, I would recommend, how do you learn this stuff? It's quite a bit. Go over all the dynamic programs that we've done in class. Okay? Go and read all of them. If you've solved the coding homework, which is not that difficult, go and look for the dynamic program structure there. You'll see it. Right? Presumably, you've started at n, you're looking up some other entries of the table to fill it up. So look for that structure and write it out as a recurrence, not for the homework, but just for your own sake. And if you write it out, you'll actually see what the running time and all of that is. So do that process. Then start doing the homework problems. And again, always try to look for this structure there. You can look at CLRS. I'll see if I have more questions to post, and I'll post some of those. Some might be easier, some might be harder. The homeworks, they're not that difficult once you understand this structure. Okay? And again, the way to apply it is just like, I don't know, this is the way that I apply data structures, right? I don't figure out looking at the problem, oh, this is the data structure. I have a list of data structures. I keep flinging each one of them and saying, does this work? Does this work? Does this work? And it's the same with dynamic programming. You have this mental model and you say, oh, is this going to work or not? I think that's usually the approach that I use for algorithms, not like suddenly I look at a problem and I guess, oh, this is dynamic programming. It's like you have this list of tools and you keep flinging each one of them at it, and then you'll kind of see, okay, this works or this doesn't work. Does that make sense? Yeah, I wouldn't be that stressed out about learning this. I mean, it takes some time, but I promise you, give it like a couple weeks, you do the homeworks, you'll learn it. It's not rocket science. Or okay, maybe it is rocket science, but whatever. It's computer science. Any questions? Okay, so again, as I said, the next lecture, that's going to be online. And so I also will not be able to hold office hours because I am traveling. So next week I'll cancel office hours. I'll make announcements to that effect. Thursday. And as I said, I will give an option for resubmitting homework 2. For, if you see your error, I'll give detailed instructions. I don't want people to go on fishing expeditions. But, if you genuinely figure out your error and you know how to solve it, I want to give you credit for that. And anything else. So this ends dynamic programming. Next lecture, we're going to start greedy algorithms for maybe a couple weeks. And then we'll see what happens after that. Okay? All right, let's end early today. Sure. This one?